Geometric sequences and series. Recall in the previous section we defined what an arithmetic sequence is. It was a sequence that's generated when we repeatedly add a fixed number to an initial term. A geometric series, which is the concept of this section, is generated, however, when we start with a number and we repeatedly multiply this time, instead of adding, by a fixed number that we're going to refer to as the common ratio. Concretely, I'm saying the following. A geometric sequence is a sequence of the form a fixed number, and then you multiply to get to the first term. From the first term to the second term, you multiply by this number r. So you multiply by r, and then to get to the third term, you multiply by another r, and to get to the fourth term, you multiply by another r, and so on and so forth. So the successor is the predecessor times r. Okay? The number a, that number a, is called the first term, and r is called the common ratio of the sequence. So what's the why it's common ratio? Because the quotient of two consecutive terms is r, right? Because you pass from one to the next by multiplying by r, or equivalently, you can divide the successor by r to get to the predecessor. Okay. All right. And the nth term of a geometric sequence is given by this. Let me clarify why. Because what's a1? This is a1, right? Which is the first term. The second term is this guy. Okay, correct? And the third term is this, and so on and so forth. So the nth term, an, what is it? So the first term is a. The second term, you multiply by one r to get to the second term. To get to the third term, you multiply by another r. So from a to z, from the first to the third term, you multiply by r twice. To get to the fourth term, you multiply by r 3 times, and so on and so forth. To get to the nth term, you start from a and you multiply by r n minus 1 times, correct? You can check when n is 1, right? When n is 1, we're talking about a times r to power 1 minus 1, which is 0. R to power 0, in this discussion, r is not supposed to be 0. So any non-zero entity to power 0 is 1. So you get a. And so on. When n is 2, this is going to be r. And then this is going to be a times r, which is this, and so on and so forth. Okay. So the nth term of a geometric sequence is given by this recipe. Let's do a problem. This is section 11.3. This is on page 1036. On page 1037, let's do number, let's do 12. So in this problem, we need to determine if this sequence is geometric or not. And if so, we need to determine the value of r. Okay, so let's take this sequence. All right, so to be geometric again, the quotient between any two consecutive terms, it has to be a fixed number, which is the common ratio. Let's see. So, in other words, do we have this property for all n? Let's check this. What's the ratio between the first term and the second term? The first term here is 5, right? So the first, let's write this down. A1 is 5. A2 is minus 5 over 3. They gave us the second, and the third, and the fourth. The third is 5 over 9. And the fourth is negative 5 over 27. So, is the quotient between any term and its predecessor, is it a fixed number throughout this process to go from one term to its successor? Let's see. So what's the quotient between a2 and a1? Well, the quotient between those two is, well, a2 is minus 5 over 3, and a1 is 5, and this quotient is minus 1/3. So if this is a geometric sequence, then the common ratio is gonna be minus 1/3. Let's check. To go from here to here, we multiply by negative 1/3. We know this because we just did it. Now, to go from here to here, do we multiply also by minus 1/3? Does this guy, or is this guy times this 5 over 9? Yeah, the minus times the minus is a plus. 5 times 1 is 5. 3 times 3 is 9. So yeah, to go from here to here, we multiply by this number minus 1/3. How about to go from here to here? To multiply, to pass to this, if this is a sequence that's geometric, I should multiply this number by this guy, which is supposed to be the common ratio. 5 over 9 times negative 1/3 is negative 5 over 27. So this is a geometric sequence. So this is a geometric sequence. Let's make the case. To be a geometric sequence, you can also look at it this way. The nth term should be the first times r to power n minus 1. Well, the second term, or okay, so a is 5, right? A is 5. This is the first term. A is the first term in the discussion of the definition, right? So a is the first term in the discussion of the definition. So a1 can be thought of as 5 times r, which is the common ratio, to power 1 minus 1. Okay? And the second term is 5 times minus 1 over 3 to power 2 minus 1. So it is verifying this so far, right? We know it's going to verify all of it because we went through this process and it turned out to be a geometric sequence. Okay? All right. And how about the third one? The third one is the first term times minus 1 over 3 to power 3 minus 1. So this is still holding, right? So this is being the 5, and r is being the quotient, minus 1 over 3. And the n in this context, in this context here, is a 3 minus 1. And the last one is 5 times minus 1 over 3 to power 4 minus 1. Correct? So it still verifies this. In other words, to go from one term to the next, you multiply by minus 1/3, which is a common ratio to all of this pattern. All right, moving on to the next example. Let's do 14. So same question, but now for this sequence. What's the ratio between, is this a geometric sequence? If this is a geometric sequence, you should go from one stage to the next by multiplying by the same common number, the common ratio, right? To go from here to the next, you multiply by 2, right? Because 14 divided by 7 is 2. So do we get the same thing? If we do the same thing, do we get the same number that's occurring here? In other words, if we multiply 14 by 2, do we get 42? Well, 14 times 2 is not 42, right? It's 28. So definitely we don't get this. Okay? So this is not a geometric sequence. Because to be a geometric sequence, to go from one term to the next, you should multiply by a common number, and that number is called common ratio, which is referred to as r here. Okay? All right, so this is not, so no, this is not a sequence that's geometric. And the reason is, since the quotient between a2 over a1, so the quotient a2 over a1, which happened to be what? It happened to be 2, right? Is different than the quotient between A3 over A2. Correct? A3 over A2. 42 divided by 14 is not 2. So this would be the reason why this is not geometric. And in the previous context, the previous number, it was geometric, correct? So let's actually formulate this. So yes, this sequence is geometric. And the common ratio is it was minus 1/3 at the time, right? Okay. Geometric sequences occur naturally. And here's a simple example. Suppose that you have a ball with elasticity such that when it's dropped, it bounces up 1/3 of the distance it has fallen. So for instance, if you drop the ball from height 2 meters, it's gonna bounce up to a height of 1/3 of that, which is 2 over 3 meters. 2 over 3 meter. So pictorially, if you drop the ball from this height, it's gonna go down. After the first bounce, it's gonna reach the third of that height, the 2 meter, which is 2 over 3 meters. 2 over 3 meter, correct? So you get to this point. And then on its second bounce, it's gonna hit the ground, and then it's gonna reach the third of 2 over 3, which is 2 over 9 meter, right? And so on and so forth. So each height is gonna be the third of the preceding one. So you're describing a geometric sequence. And the question is, what's hn, the height of the ball after the nth bounce? Well, since this is a geometric sequence, it's gonna be, I'm going back to the definition here of the geometric sequence, it's gonna be the nth term of the geometric sequence, which is given by this. It's gonna be the first term times the common ratio to power n minus 1. Correct? So hn, which is the height after the nth bounce, it's gonna be the first term a times r, which is the common ratio, which is 1/3 in this case, right? Because each term is 1/3 of the preceding one, to power n minus 1. And if you multiply these terms, 3 times 3 to power n minus 1, this is 3 to power n, correct? And so on and so forth. All right. So this would be in meters, the height of the ball after the nth bounce. All right, let's take an example. And let's do one of these. How about 22? So the question here is, write the first 5 terms of a geometric sequence an based on the given information about the sequence. So they need the first 5 terms. Well, they told us this is a geometric sequence. So we know that an is equal to the first term times r to power n minus 1. Correct? There's no a here, so I'm going to write, instead of a, I'm going to write first term, because this is what a represents in the formula, right? So first term times r to power n minus 1. What am I saying here? I'm just using the definition, this one, right? The nth term of a geometric sequence is the first, correct? The first times the common ratio to power n minus 1. That's exactly what I used in this little discussion here. Okay? All right. And then what's a1? A1 is 80. That's the first term. A2 is the first term, which is 80, times r, which they told us r is minus 4 over 5, to power, when n is 2, that's going to be r to power 1, right? So it's going to be r to power 1, so r. So we get this. And what is that? 80 divided by 5, that's 16. 16 times negative 4 is negative 64, right? So the second term is negative 64. How about the third term? The third term is the first times r to power n minus 1. So r to power r minus 1. In this case, r is 3, right? So it's going to be r to power 2. Which is the same as this guy, the preceding one, times the common ratio, which is minus 4 over 5. Right? So you get, it's the same as minus 64 times the common ratio, which is minus 4 over 5. And minus times minus is plus. 64 times 4, that's 256 divided by 5. And so on and so forth. So let's do, they need the first 5 terms. Let's do the fourth. That's going to be the first times r, which is minus 4 over 5, to power, so in this case n is 4, right? N is 4, so that's going to be r to power 4 minus 1, which is to power 3 then. Which is the same as the third term, which was this, times the common ratio, correct? So, and the common ratio here is minus 4 over 5. This is a negative number, and that's a positive number, so that's going to be the answer, the product is going to be negative. And 256 times 4, that's 1024 divided by 5. Divided by 5 times 5, which is 25. Okay, so that would be the fourth term. And you still need to find the fifth term, which is 80 times minus 4 over 5, which is the common ratio, to power 4 this time, because n is 5, and 5 minus 1 is 4. Which is the same thing as multiplying the preceding one by the common ratio. And the common ratio here is minus 4 over 5. Okay, and how much is this? This is a positive answer for sure. Minus times the and minus. 1024 times 4, that's 4096, divided by 25 times 5 is 125, right? So we get this. So this is an example of a geometric sequence whose common ratio is negative, and you realize that the terms are alternating in sign, right? So positive, negative, positive, negative, positive, and so on and so forth. So this is an example of a geometric sequence which has common ratio which is negative. Okay, it alternates in signs. Okay, this is one example from this group of problems. Write a formula for the nth term of the geometric sequence. And let's go for 30. So we need to write a formula for the nth term of this geometric sequence. And as you know, as we discussed here in this definition, a geometric sequence is fully described based on its first term and its common ratio, right? If you know its first term and its common ratio, you're done. You just have, this would be the recipe of its nth term, right? Okay. Alright, so, and here, the first term is simply 18 over 5, right? This would be the first term. Because we know that an is first term for a geometric sequence. It's first term times common ratio to power n minus 1. Correct? And this is for all n. For all natural number n. Okay, so we got this. We got this. This guy is this guy, right? 18 over 5. How about R? They told us this is geometric. So they told us, in other words, that the quotient between any two consecutive number or any two consecutive terms is a fixed constant. That constant is R. All right, let's find what R is. Well, R is equal to, just pick any two consecutive terms and just take the ratio between them, because they told us this is a geometric sequence. So let's choose the first two. So minus 6 over 5 divided by 18 over 5. Correct? Clearly the common ratio is going to be negative because the sign is alternating, right? This is a sequence that alternates in sign. So clearly the common ratio is going to be negative. And what is this thing? If you divide by the 5s, right? Let's actually do it. So this is minus 6 over 5 divided by 18 over 5. And as usual, we're gonna rewrite division in terms of, we're gonna write this this operation division in terms of multiplication. And dividing by something is the same as multiplying by the reciprocal of the thing, right? Okay. 5 divided by 5, that's a 1. 6 divided by 18, that's 1/3 here, right? So this is minus 1 over 3. So the common ratio is minus 1 over 3. As such, so we found this, and we found this. So we can describe the nth term of the geometric sequence in number 30. So thus, the nth term of the geometric sequence given here, which is 18 over 5 minus 6 over 5, 2 over 5 minus 2 over 15, and so on and so forth, is given by this. But now we know what first term is and what R is. So it's going to be AN is equal to the first term, which is 18 over 5, times the common ratio to power n minus 1, which is this guy to power n minus 1. Okay? So this would be the nth term of the geometric sequence given here. Let's do now number 36. The question here is, find the indicated term of a geometric sequence from the given information. So we have a geometric sequence and we're given the first term and the second term here. And the question is to find the fifth term. So they told us this is a geometric sequence. Okay. So which means they told us, let's visit the definition again. They told us that the nth term of the geometric sequence looks like this, right? So since it's a geometric sequence, we know that the nth term of that sequence is gonna look like this. All right. So the nth term, we know it looks like this: the first term times the common ratio to power n minus 1. Okay, and we've been labeling the common ratio by R. Okay, so they gave us A1. So this is 16, and A1 is the first term, right? So this guy is 16. And they gave us A2. Well, and this should entail that we should be able to discover what R is. Well, don't forget, R is the common ratio, which means it's the quotient between two consecutive terms. Well, I have two consecutive terms here, A1 and A2. So this means that R is equal to A2 over A1, right? The second term divided by the first term. And in this case, A2 is minus 12 and A1 is 16. And if you perform this division, this is a negative entity. If we divide upstairs by 4, we get 3. If we divide downstairs by 4, we get 4. So therefore, the nth term, right? So an, the nth term of the geometric series is given by first term, which is 16, times the common ratio, which is minus 3 over 4 to power n minus 1. Right? This is the nth term of the geometric series. And this is for all n, for all natural numbers n. What do they want? They want us to find the fifth term. So they want us to find the fifth term. Well, the fifth term is when n is 5. Correct? So the fifth term is when n is 5. That's going to be 16 times when n is 5. So that's the same thing. It's going to be 16 times minus 3 over 4 to power 5 minus 1. And how much is this? 16 times negative 3 over 4 to power 4, right? 5 minus 1 is 4. And this is equal to 16 times negative 3 to power 4 divided by 4 to power 4. And this is equal to, well, 4 squared is 16. So downstairs I'm going to be left with 4 squared, which is 16. And negative 3 to power 4, that's certainly positive. 3 times itself 4 times, that's 9 times itself 2 times, which is 81. So the fifth term turns out to be 81 over 16. Alright, so let's now move on to a different problem. And let's do a problem from this group. How about 48? Here we have A3 and A6, so we have the third and the sixth term of the geometric sequence, and they told us to find the first and r, the common ratio. Okay, so we need to find the first term and the common ratio, given that we know the third term and the sixth term. So let's do this. Well, since we know that this is a geometric sequence, we know that the nth term is gonna be the first, so a1, times the common ratio to power n minus 1. So we know this, and this is for all n, for all natural numbers n. Why? Because we know that the sequence is geometric. So let's be very specific on this. So since the sequence is geometric, let me make room for myself. So since the sequence is geometric, we have, by the definition above, that the nth term looks like this, correct? This is what we have. And this is for all n. Now, we know A3, right? So on one hand, A3 is known, which is 45. We know that. And on the other hand, A3 is given according to this recipe, which is A1 times R to power 3 minus 1. Okay? So this is on one hand, and this is on the other. Okay? So A3 is on one hand 45, they told me this, and because it's the third term of the geometric sequence, so it's gonna be the first times R to power 3 minus 1. And what does this entail? This forces A1 times R squared, right? 3 minus 1 is 2, to be 45. Okay. Similarly, I know that A6 is on one hand negative 243 divided by 25. So this is on one hand again. Let's keep the color the same. And on the other, we know that this is, since this is the sixth term of the geometric sequence, I know it's going to be a1 times the common ratio to power 6 minus 1. Correct? So we get this. And this entails that a1 times r to power 5, right? R to power 6 minus 1. 6 minus 1 is 5. Should be equal to negative 243 divided by 25. Okay? And what's the question again? The question was to find a1, which is the first term, and the common ratio of this geometric sequence. Okay? So we need to find a1 and r. Well, I have this up to this point. This is what I have, right? So that's what I have. I have that a1 times the common ratio squared is 45, and a1 times the common ratio to power 5 is equal to this much. And I need to find a1 and r. Please pause the video and try to think about this. How I can get my hands on a1 and r. The way I'm going to proceed is I'm going to take, let's say, this guy divided by this guy. Okay? So a1 times r to power 5 divided by a1 times r2. A1 for sure a1 cannot be 0, right? Because if a1 is 0, this product becomes 0. And likewise here, so which is not the case, correct? So if a1 is 0, then a1 times, for example, r squared is going to be 0, which is not the case. So certainly a1 is not 0, and as such, dividing by a1 makes sense. Similarly, r cannot be 0, because if r is 0, this product should be 0. So this is why this is meaningful. On one hand, this is equal to, what's a1 r5? It's that guy. Correct? This is the numerator. Divided by this guy, which is 45. Correct? So one more time. I took this divided by this. That's this side. And the numerator here is this piece. I got it. And that guy downstairs is simply 45. Okay? All right. Now, on the other hand, what do we know about this? What is this? If you simplify by a1 and you simplify by r squared, you get r cubed. Correct? One more time. a1 divided by a1, that's 1. r5 divided by r squared, that's r cubed. This is why I wrote the r cubed. So at the end of the day, r cubed should be this much. Correct? So r cubed should be this much. Okay, and what is that? If we try to simplify this, what do we get? This is the same thing as minus 243 divided by 45 times 25. Alright, so let's simplify this a little bit. 243 divided by 9 is 27, and 45 divided by 9, that's 5. So we get here negative 27 divided by 125, right? Which is negative 3 cubed divided by 5 cubed. Correct? Okay. So if r cubed is this much, therefore r, which is the third root of r cubed, is gonna be the third root of this entity, which is minus 3 over 5 cubed, and that's simply minus 3 over 5, right? The third root of an entity cube is the entity itself. So r is this much. So we know what r is. Now, if we know what r, can we find the first term? Sure. Either from here or from here we can do it, right? Let's do it from here. So we know that a1 times r squared is 45. So since a1 times r squared is 45, we get that 45 should equal a1 times the square, right? The square of r. That's how much r is. So minus 3 over 5. So one more time. Because of this guy, a1 times r squared is 45, but at this point I know what r is. This is how much r. So I'm gonna put it here, and then a1 times the square of this r, I'm gonna get 45. That's exactly what I said here. That's exactly what I said. Okay? So a1 times r squared is equal to 45. So a1 times r squared is equal to 45. Okay. And now we're gonna solve for a1. That is to say, 45 is equal to a1 times the square of negative 3 over 5 is 9 divided by 25. Correct? Is 9 divided by 25. And now if we divide through by 9, this becomes a 5, and this becomes a 1 over 25. And this tells you that a1 should be 5 times 25, which is 125. Correct? So that's how much the first term is. So a1 at the end of the day turns out to be that guy, and r turned out to be this. And this was the question. We needed to find the common ratio and the first term given the third term and the sixth term. So what was the strategy again? We know it's a geometric sequence, so we know how the nth term looks like. And because we know the third and the sixth, that gave us two equations and those two unknown, a1 and r. I divided this a1 times r5 by a1 r squared. That gave me r cubed on one hand. On the other hand, this divided by 45, which turned out to be this guy. So r cubed is this much. R is going to be the third root of that, which is minus 3 over 5. And once you know r, you can figure out a1. Either from this equation or from that equation. Either or. So a1 times the square of r, which is the square of this, is 45. As such, we unraveled it and it came out to be 125. Let's look at the nth partial sum of a geometric sequence. So let's say I have the following geometric sequence, whose first term is a, and then the second term is a times r, and the third term is ar squared, and so on. And the nth term is the first term, which is a, times the common ratio, which is r, to power n minus 1. We know this, right? So let's look at the nth partial sum. Remember what nth partial sum is. We talked about partial sums in the previous section when we talked about arithmetic sequences. And the nth partial sum is simply the sum of the first n terms of a sequence, right? So if we're talking about the nth partial sum, it's going to be, for this sequence, it's going to be the sum of the first n terms. So it's going to be the sum of all of this, and that's labeled as S sub n, right? So it's the summation of the terms, all those terms, a times r to power k minus 1, where k ranges from 1 all the way to n, right? So when k is 1, you get the first term. When k is 2, you get the second term, and so on and so forth, all the way to the nth term when k is n. So you get this. Okay. So now, like exactly the same as we did for the arithmetic sequences, since we're adding, right? We are adding numbers produced. Each of these terms is produced according to a fixed pattern. We multiplied from one to the next. Right, from one to the next, we multiplied by r, the common ratio. Since we're adding such numbers which are constructed based on a fixed pattern, definitely this Sn must have a pattern, or by pattern here I mean a formula for finding the sum. Let's try to discover this formula. So we're gonna start by rewriting what Sn is. So Sn is simply a plus ar plus ar squared plus ar cubed plus etc. all the way to a to power r minus 1. And what I'm gonna do is, since the common ratio is not 0, I'm gonna multiply by r here. I'm gonna multiply both sides of this equation by r, and I'm gonna get an equivalent equation, and it's gonna read as follow. So I'm multiplying this side by r and this side by r, so everybody here is gonna be multiplied by r. So r times a is ar, right? So I'm multiplying this by r, we get ar. I'm multiplying this guy by r, I get ar squared. Right? I'm multiplying Sn by r. Well, each term of the Sn is gonna be multiplied by this number r. Well, if you multiply r by the first term, you get ar. If you multiply r by the second term, you get ar squared. If you multiply r by the third term, you're gonna get ar cubed, and so on and so forth. And if you multiply r by the last term, you're gonna get a times r to power n, correct? And the previous term is gonna be a times r to power n minus 1, and this is when you multiply r by the second to last term in the Sn, and the second to last term here is a times r to power n minus 2. And if you multiply r by this, you get exactly that, correct? So a times r to power n minus 2 times r, so it's going to be r to power n minus 1, which is here. Okay? All right. And actually, let me just keep this in your notes. Very good. So now, what I'm going to do is I'm going to subtract the bottom from the top. I'm going to subtract the bottom from the top, and I'm going to get Sn minus Rsn is equal to, this is the left side, this guy minus this guy. On the right side, I'm gonna get all of this minus all of that. So this minus itself is gonna be gone. This minus itself is gonna be gone, and so on and so forth. So all of these are gonna collapse, including this last term with this guy. And the only survivors and the difference are gonna be this minus this, correct? So you're gonna get a minus a times r to power negative 1, and this is again because we subtracted the left sides together and the right sides together. This minus this, they're gone. Let me just leave it for you here. And this minus that, they're gone. This term minus this term, they're gone. And this guy here minus, it's gonna happen here, right? So right before, correct? So I missed the dots here. And then and then this is gonna cancel with this guy, and then at the end of the day, as I mentioned, the survivors are gonna be this and that. So it's gonna be a minus a times r to power n. Oh, I copied it wrong, so it's gonna be this, right? Okay. All right, and that's equivalent to saying Sn minus Rsn. If you factor out Sn, you're gonna get 1 minus R equals, and let's factor out A here, we get 1 minus Rn. Correct? If you factor out A on this side and Sn on this side. And if we suppose that R is not 1, so if R is not 1, this means R minus 1 is not, this means 1 minus R is not 0. Then we can divide both sides by 1 minus R, if we suppose that R is not 1. Correct? This becomes non-zero, and as such I can divide by this entity. And I obtain Sn is equal to A times 1 minus Rn divided by 1 minus R. So what have I done? I divided both sides by 1 minus R, and I can do so because I'm supposing now R is not 1. As such, this is a non-zero entity because R is not 1, and we can divide by this entity as such. So we get this divide by 1 minus R, which is Sn, and this guy divide by 1 minus R, which is what you see here. So this is the formula I was after. This is a formula of the nth partial sum of a geometric sequence. And this is recorded on the second page, or the next page here, as you see on the screen. So for the geometric sequence an, which is equal to a times r minus 1, this is the general term, the nth term. The nth partial sum, which is that, is given by this formula that we just discovered above, and this is when r is not 1. Correct? You see this assumption, which was needed in the process above, was needed here. So it's embedded in the property. Okay? It's part of the property. And the proof of this property is the discussion right above that. Okay. All right, let's do a problem. This is on page 1038, and let's do number 52. The question is, we need to find the sum of the geometric series, if possible. So we need to find the sum of those terms which are coming from a geometric sequence. Okay? So we have a formula for that. We just discovered it right above. And the formula says the sum of the first n terms of a geometric sequence is the first term. This is the first term, right? So it's the first term times the quotient 1 minus common ratio to power n divided, and this is the same n, by the way, right? Divided by 1 minus the common ratio. So here I have the seventh partial sum of the geometric series, and because this n is 7, so I'm adding the first 7 terms of a geometric sequence. In this case, the first term is 2, correct? The first term is 2, and the common ratio is 3 over 4. Okay, according to this property above, so this is equal to, by the property above, correct? And this is equal to what? This is equal to a, which is the first term, and the first term here is 2, correct? What's the first term here? Is when j is 1. When j is 1, this becomes 0. 1 minus 1 is 0. As such, this term becomes 1, and 2 times 1 is 2, correct? So it's the first term, which is 2, times 1 minus common ratio, which is 3 over 4, to power n, and n is 7 here because I'm adding the first 7 terms of the geometric sequence. So this is 7 divided by 1 minus r, which is 3 over 4. Correct? So I just copied this formula that we just discovered, when the first term is 2 and r is 3 over 4. And we compute this, and what do we get? 2 times 1 minus 3 to power 7 is 2187 divided by, let me make some room here, so divided by 4 to power 7, which is 16384, divided by this guy downstairs. Let's make the same denominator, so 4 minus 3 over 4. Okay. Alright, and then this is equal to 2 times, let's have the same denominator upstairs, which is 16384. So let's have it here, 16384 minus 2187. Correct? So the same denominator. Divide by 1 over 4 downstairs, correct? 1 over 4, because 4 minus 3 is 1. Okay, and what's 16,384 minus 2,187? This is 14. So 2 times 14,197 divided by the 16,384 divided by 1/4. Okay, let's move this to the side. And what is that? This is equal to 2 times that, divided by 1/4 is the same as multiplying by 4. Okay. Alright, let's see now if we can simplify this. This guy here upstairs is a prime number, 14,197. 16,384 is divisible by 8, right? Divisible by 4 times 2, and this is going to be 2,048. So that's a prime, and this is smaller than that, so this is in reduced form then. 14,197 divided by 2,048. Okay. Alright, so the sum of those 7 terms and this geometric series, or equivalently the sum of the 7 terms of the sequence whose first term is 2 and its common ratio is 3 over 4, is actually this quotient. Alright, let's move on to the next problem. Let's do number 56. Still the same question. We still need to find the sum of the geometric series. And here we have the terms are 4, 12, and so on. So these are the terms of the geometric sequence 4, 12, 36, and so on, all the way to this number 78732. Okay, so these terms belong to this geometric sequence. They told us this is a geometric series, so this is its terms are going to come from a geometric sequence, and we know how to add the first n terms of a geometric sequence, right? And this is given by this formula that we just discovered above. Provided we know the first term, common ratio, and the rank that we are stopping at, right? So the rank that we are stopping at. Well, over here we have this. We don't know what this guy corresponds to in terms of the sequence, right? So my point is, this is, if this is A1, this is A2, this is A3, this is A what? right? I'm trying to discover what's the rank of this guy 78,732. Okay? Once you discover the rank of that, you can find the nth partial sum based on the property that I just alluded to earlier. Okay? Alright, let's do that. We know that a sub n, which is the nth term of a geometric sequence, is given by the first term times the common ratio to power n minus 1. We know that. This is an earlier property. And what's the first term in this context? What's the first term? It's the 4, correct? This is a 4. How about the common ratio? Well, they told you this is a geometric sequence. So the quotient between any two consecutive terms is going to be this common ratio that I'm looking for. And we only have those two as common ratio as consecutive terms, and those two. The quotient between this 12 and 4 should be the same as the quotient between 36 and 12. Let's choose which one we want to do. They're going to be the same anyway. So let's take 12 over 4, let's say. And this is simply 3. Correct? So the common ratio here in this case is 3. So this means that an, any term of the sequence, is written as 4 times 3 to power n minus 1 for any n, right? For any term. For any term. The question now is, we need to find let's say k such that a sub k is equal to 78,732, right? We need to find a sub what that thing is. We need to find the rank of this term, and I'm calling this question mark k in this context, okay? In this little discussion here. So I need to find the rank of this term. By rank I mean this index. So I need to find the rank of this term. A sub what is this guy? Because this k is gonna be part of, it's gonna be, so this k, this becomes a1 plus a2 plus a3 all the way to ak, which is the kth partial sum, right? Which is the kth partial sum. And then I use the property that's in the property above, this one, where n is k. Correct? That's the strategy of the plan. Okay, so let's do that. So AK is this much. I need to find the K. Well, AK is 4. AK is equal to 4 times 3 to power K minus 1. Right? AK is 4 times 3 to power K minus 1. This is on one hand. On the other hand, AK is this guy. 7, 8, 7, 32. So on one hand, AK is this. On the other hand, it's this. So these should match. 4 times 3 to power K minus 1 is equal to 7, 8, 7, 32. Don't forget, we are after K. Alright. This means what? This means 3 to power K minus 1 is equal to 7, 8, 7, 32 divided by 4. I'm dividing both sides by 4 now. And this is 19, 6, 83. Okay? I want to find K. What you can do here is you can observe that this guy is equal to 3 to power 9. So 3 multiplied by itself 9 times yields 19,687. That is to say, So this thing becomes equivalent to saying 3 to the power k minus 1 is equal to 3 to the power 9. Correct so far? So one more time, what am I trying to do? I'm trying to find the k so that the kth term becomes 78,732. In other words, I'm trying to determine the rank of this. Okay? So what I've done is, I know that ak on one hand is this, but on the other hand, based on that property, ak is gonna be 4 times 3 to the power k minus 1. So this guy must be equal to that guy. This is what you see here. And now if you divide both sides by 4, so it's gonna be 78,732 divided by 4, which is gonna be this, and we made the observation that 3 to the power 9 is that guy. So we get down to 3 to the power k minus 1 is equal to 3 to the power 9. And here we're gonna use an exponential, the exponential function. The fact that the exponential function is a one-to-one property, is a one-to-one function, right? So what I'm gonna use here is that ax equals ay when the base a is positive and different than 1, right? The exponential function is one-to-one, which means ax equals ay is equivalent to saying that x is equal to y. That's what I'm using here. So I have the same base, right? The a is the 3, and then according to this property, clearly the 3 is positive and different than 1. As such, the powers must match. This is exactly the same as saying that the powers must match. So k minus 1 should be 9, which means that k should be 10. Correct? So one more time, because of this property here, those exponents must match. And this is equivalent to saying that, right? They are equivalent. Bottom line, k is 10. So which means that this guy here happened to be the 10th term of the sequence. So this is the 10th term of the sequence. So if this is a1, this is a2, this is a3, and so on, and this is ak, we just found in the discussion below that this k happened to be 10. Correct? This is what we just found. As such, what they gave us is the sum of the first 10 terms of this geometric sequence. Okay? So thus, let's keep going with this. So thus, four plus 12 plus 36 plus so on plus 78, 732 is equal to the sum of the first 10 elements in the geometric sequence, and this is denoted by s sub 10. Correct? By s sub 10. And based on the property above, what's the sum of the first n terms of a geometric sequence, which is the nth partial sum, is given by this property. It's first term times 1 minus common ratio to power n divided by 1 minus common ratio. Let's do it. So S10 by the property above, this is equal to the first term, and who's the first term? It's the 4, right? It's the 4 times 1 minus the common ratio to power 10. That power sits here. This is why I was looking at it, right? Or trying to find it. So it's the 10, and this is the r that sits here. And who's the r in my context? Which is the common ratio. The r is 3. So the r is 3 divided by 1 minus the r. Okay, so one more time, we use the property above, which says Sn, the nth partial sum of the geometric series, is equal to the first term times 1 minus the common ratio to power n. So if this is k, that's going to be k. If this is n, this is going to be n, and so on and so forth. So whatever this guy is, it's going to sit here. Divide by 1 minus that common ratio. And now it comes down to finding what this number is. So this is equal to 4 times the quotient 1 minus 3 to power 10. Well, 3 to power 10 is 3 to power 9 times 3, so it's going to be this number times 3, which is 59,049. And downstairs I have 1 minus 3, which is minus 2. Okay? Alright. This numerator is negative 5948, and 4 divided by negative 2, that's gonna leave you with negative 2 upstairs. So it becomes negative 2 times that entity, negative 59048, and this is equal to 118,096. Okay, so at the end of the day, the sum of the first, or those terms, which happen to be the first 10 terms of this geometric sequence, turned out to be this number, 180,096. The next concept in this section is about infinite series. We know what a series is. It's a sum of terms. For example, when we talked about the nth partial sum of a sequence, we added the first n terms of that sequence, and that was a finite series at the time. Now we're going to talk about an infinite series. So what's an infinite series? It's an infinite sum. It's an expression that can be written as such, and it means that you are adding infinitely many terms of the sequence ak, let's say. Okay, so in sigma notation you write it as such, where the index k ranges now from 1 to infinity, so the k doesn't have an upper bound, right? It keeps going forever. For finite sum, for finite series, we used to truncate this. We used to stop at a certain rank. Over here we're gonna keep going. So a1 plus a2 plus a3, right? So you let k vary through the natural numbers all the way to infinity. So the 3 dots here mean that this addition continues indefinitely. Okay, so this is what an infinite series is. Now, what type of meaning we can associate to an infinite sum? This is the next question. Let's read the following discussion. It seems at first that it's not possible to add infinitely many terms and arrive at a finite number. But let's take a closer look and consider the following situation. Suppose that you have a cake and you want to eat it by first eating half of it, then eating half of what remains, then again eating half of what remains. This process can continue indefinitely because at each stage, some of the cake is going to remain. So pictorially, suppose that the cake is given by a disc. At first, the first stage, you eat half of it, then you're left with another half. You eat half of what remains in the next stage, so you eat a quarter of the entire cake. And then you're left with a quarter, so you eat half of that, which means 1/8 of the entire cake. And then you're left with an eighth of, or 1/8 of the entire cake, so you eat half of it, which means you're eating 1/16 of the entire cake, and so on and so forth. Does this mean that it's impossible to eat the entire cake? Of course not. Let's take a look actually of what you've eaten from the cake. So the first step, you ate half of it. Then you eat 1/4 of that. So after the second step, all the way to here, you've eaten this. And then so on and so forth. So you eat the 1/8 after that, 1/16, 1/32, and so on and so forth. So you add them up, and we can represent it by this infinite sum. This is an infinite series, and we know two things about it. The first, from the figures above, it's clear that no matter how many terms of the series we add, the total will never exceed 1, right? So no matter how many pieces you eat based on the pattern just described above, you will never go beyond the cake, for sure. Correct? So this is the first observation. The second, the more terms of the series we add, the more you eat of the cake, the closer you are to eat the entire cake. So the closer the sum is to 1. Again, this is illustrated by the figures here. Okay? So this suggests that the number 1 may be written as the sum of infinitely many smaller numbers. That is to say, I can rewrite 1 as 1/2 plus 1/4 plus 1 over 8 and so on and so forth plus 1 over 2n. So I can write 1 as the sum of powers of half. Okay? To make this more precise, let's look at the partial sums of the series. Remember, partial sums, we are talking about we are truncating the infinite series at one rank at a time, right? So we're talking about cumulative sum. So S1, the first partial sum, is just the first term. S2, which is the second partial sum, is the sum of the first two, and this happens to be 3/4. S3, which is the sum of the first three terms, is 7 over 8. And in general, Sn, the sum of the first n terms, turns out to be 2 to power n minus 1. We've seen this sum before in an earlier section. And this is equal to 1 minus 1 over 2n. And now let's make the following observation. As n gets larger and larger, what happens to 1 over 2n? 1 over 2n decreases to 0, right? So as n blows up, 1 over 2n is gonna shrink, is gonna decrease to 0. So intuitively, Sn gets closer and closer to 1 because this term here is going to 0. Correct? So Sn can be written as, or we can write that Sn gets closer and closer to 1 as n becomes large. In general, if Sn gets close to a finite number s as n gets large, we say that the infinite series converges or is convergent. The number s is called the sum of the infinite series. So in this case s was 1, right? In this case s was 1. The sum of the series is 1. So of course we cannot add infinitely many terms, but the idea is we call S the limit or the total sum of the infinite series, provided by adding sufficiently many terms of the series, we can make the partial sum as close as we wish to the limit point S, to the total sum. So for example, here the total sum was 1. The more terms we add, right? The more terms we add, which means that we are talking about larger nth partial sum. In this case, this guy shrinks, and the closer we get to 1. Correct? So one more time. By adding sufficiently many terms of the series, so the larger the nth partial sum is, the larger the rank of the nth partial sum is, which means the more we are adding, the more terms we are adding of the series, the closer we are making the sum or the partial sum to that point, to that limit number s, which is 1 in this case. Okay? If this situation happens, we're gonna call that number the total sum of the series. Okay? And we call the series a convergent series. An infinite series that does not converge is said to diverge. Okay? Alright, so this is the concept of infinite series. We're going to talk about infinite geometric series that the geometric aspect that we've been talking about in this section, well, it's still an infinite series. So by this I mean we keep adding forever, but each term of that sum looks like a times r to power n minus 1, correct? So it looks like a term coming from the geometric sequence. So what's an infinite geometric series? It's an infinite series whose terms are coming from a geometric sequence. Okay. Now to find the sum of an infinite geometric series, we can use the same reasoning that we used earlier when we found the nth partial sum of such a series. So let me take you back to that page. This was the sum of a geometric series, right? When r is different than 1. So I'm gonna copy this, and let's take it there and make a discussion. So the nth partial sum of a geometric series is given by this. So let's paste it here, and let's make a quick discussion here. So a was the first term, right? So this guy was the first term. It's the first term of the sum. So now, what did we say the total sum of the series? The total sum is if we manage to have the Sn, the nth partial sum, getting closer and closer to a finite number by adding sufficiently many terms of the series, then we call that number, that limiting number, S, the sum of the series. Well, it can be shown here that if R, so it can be shown that if R is an absolute value less than 1, what does this mean? That is to say, if R is between -1 and 1, strictly taken, Rn approaches 0 as n approaches infinity. So as n becomes large, Rn goes to 0 if R is between -1 and 1. Let me try to convince you. If you need the entire proof of that, definitely contact me to explain it to you. But let me just convince you when R is between 0 and 1. When R is between 0 and 1, we're talking about the exponential function with base between 0 and 1, and that exponential function looks like this. Right? So this is Rn. I'm thinking about the horizontal axis as being the n-axis, right? So as n becomes large, if the base r here, I'm supposing r is between 0 and 1. I'm just talking about when r is between 0 and 1. So the Rn's, these y values, right? These y values of the function Rn are getting closer and closer to 0, right? These values are shrinking. Okay, so this is just when the base is between 0 and 1, but this actually happens when the base is between -1 and 1. If you would like the discussion between -1 and 0, the other side, talk to me. I'll discuss it with you, even though it's a little beyond the course, the current course. Okay. Anyway, so it can be shown that if that number r, the common ratio is between -1 and 1, excluding -1 and 1, then this guy is gonna become extremely small. It's gonna go to 0 as n goes to infinity. And as such, what happens to the Sn? Sn is gonna approach a times 1, so a divided by 1 minus r. Correct? So one more time, once you accept this fact that the Rn, this guy, goes to 0 as n becomes large, for those r between -1 and 1, this guy here disappears in some sense. It shrinks. It becomes it becomes extremely small, and then Sn is gonna become closer and closer to this value, a divided by 1 minus r. So as such, the series is gonna converge. Okay, So let's write this down. So it can be shown that this happens, and as such, Sn is gonna get closer and closer to a divided by 1 minus r, which is the first number divided by 1 minus the common ratio. And this is the result. This is the result I'm recording on the next page. So this result reads as follows. If the absolute value of the common ratio is less than 1, that is to say if r is between minus 1 and 1, the common ratio, then the infinite geometric series converges and has the sum this. So this becomes under this assumption, this becomes a over 1 minus r. That's what this is saying. And again, what does this equality mean? This means that by adding sufficiently many terms, the sum is getting closer and closer to this value. Okay, and this is an if and only if statement, which means if r is an absolute value bigger than 1, that is to say, if r is less than or equal to -1 or r is greater than or equal to 1, the series is gonna diverge. I hope you see, for example, when r is 1, this sum here becomes a plus a plus a plus a forever, right? And if you are adding a infinitely many times with itself, certainly the sum is not gonna be a finite thing, right? You're adding without control, so certainly the sum is gonna blow up. So it's not gonna go to a finite number. And when r is bigger than 1, you can think about the exponential function with base bigger than 1, right? So I'm talking about the function Rn. Again, this is the n-axis, and this is the function Rn. When r is bigger than 1, what happens to the Rn's? What happens to these y values? What happens to these y values? They blow up, right? So the Rn blows up as n goes to infinity. It goes to plus infinity. And as such, what happens to the nth partial sum? The nth partial sum, which used for a geometric series, which used to have this formula, Sn equals a times 1 minus Rn divided by 1 minus r. If the Rn blows up in this context when r is bigger than 1, this is gonna go to infinity as n goes to infinity, and as such, the Sn is not gonna approach a finite number, right? So the Sn is not gonna be it's not gonna approach a real number. As such, the series is gonna diverge. It's not gonna converge. Okay, so I'm giving you a little bit of insight why, at least on this side, when r is bigger than or equal to 1, why the series is gonna diverge, which means the total sum is not gonna exist as a real number. You still have to discuss when r is less than or equal to -1. It's a little beyond the course. If you need to discuss it, let me know. I'll discuss it with you as a one-on-one discussion. Okay, so to summarize, if the common ratio is between -1 and 1, the infinite geometric series is gonna converge, and it's gonna have this as its total sum. All right, let's apply this property to a problem from the book. This is still on page 1038, and let's do number 64. So we still need to find the sum of this geometric series when it's possible. All right. So this is a geometric series. They told us this, and we need to find the sum if it exists. Well, what's the common ratio in this case? Don't forget, this is an infinite series, right? This is an infinite series, and we know exactly when an infinite geometric series is convergent. It's convergent precisely when the common ratio in absolute value is less than 1. Okay, so what's the common ratio here? We can take any two consecutive terms and perform the quotient. The quotient should be common to all two consecutive terms, because they told us this is a geometric series. So let's take it between the first two. So R, which is the common ratio, is equal to A2 over A1, And in this case, it would be 6 divided by 1, which is 6. So this means, thus, the absolute value of r is 6, which is bigger than or equal to 1. And as such, the series is going to diverge, right? The geometric series is going to diverge. So by property above, by the property above, this geometric series, this infinite geometric series is divergent, and hence this sum doesn't exist. Correct? Because if the sum exists, the series is going to be convergent, and the only time a geometric series is convergent is when the modulus of the quotient of the common ratio is less than 1. By modulus, I mean the absolute value. Okay, so this is 64. Let's do another one. How about 66? So same question, but now the common ratio is going to be smaller, an absolute value smaller than 1. What's the common ratio here? The common ratio, which is r, is equal to 3 over 4, right? Correct? So if you would like to unravel what this means, this sum is actually equal to what's the first term here? When I is 1, the exponent is 0, and this becomes non-zero base to power 0, which is 1. So the first term is 1, and the second term is when I is 1. When I is 2, 2 minus 1 is 1, so it becomes 3 over 4, and then 3 over 4 squared, correct, and so on and so forth. So the common ratio is 3 over 4, right? Okay. And the absolute value of that is certainly less than 1 because it's 3/4. Since this happens by the property above, we know that this series we infer that this series, okay, they called the index I called it J. Okay, it's okay, so you can rename it to be I. 3 over 4 to power I minus 1. So this series is convergent. With sum equals what? So the sum of the series is gonna be this number, a divided by 1 minus r. And what's a again? A is the first term, don't forget this. So I prefer to just, instead of reading it a divided by 1 minus r, I prefer to read it first term divided by 1 minus common ratio. Okay. So let's do it. So first term divided by 1 minus common ratio. And in this case, the first term is 1 divided by 1 minus the common ratio, and the common ratio is 3 over 4. Whatever this number is, that's the total sum of this infinite geometric series. Okay, let's find this number. This is 1 divided by, if you do the same denominator here, you get 4 over 4. So 4 minus 3 over 4. Correct? So I'm making the same denominator downstairs. The 1 can be thought of as 4 over 4. And 4 over 4 minus 3 over 4 becomes 4 minus 3 over 4. And this is simply 1 divided by 4 minus 3 is 1 over 4. And this is simply 1 times 4 over 1, which is 4. Correct? So dividing by 1 over 4 is the same as multiplying by 4 over 1. And this is simply 4. So, bottom line, the sum of this infinite geometric series is equal to 4, in the sense that the nth partial sum gets closer and closer to 4 by adding sufficiently many terms. Okay, so this sum is equal to 4. So this sum is equal to 4 in the sense that, one more time, by adding sufficiently many terms, that the nth partial sum is gonna get as close to 4 as we want. Okay. Alright, let's go back to the book. Alright, so let's do now a problem from this group here. Let's choose 76. So we have a repeating decimal, right? 0.7888 forever. And we need to rewrite it as a fraction using the technique or the technology that we learned in this section. So 0.7888 and so on can be thought of as 7 over 10 plus 8 over 100 plus 8 over 1,000. Let me just write it cube here, plus 8 over 10,000, and so on and so forth. Correct? So this means again 0.78888. So 0.7, which is this guy, plus 0.08, which is this, plus 0.008, which is this, and so on and so forth. So this is clearly a geometric series. And I mean, I can think about this as 7 over 10. This is the first term, plus this guy. This is clearly a geometric series. I can rewrite it as sigma 8 over 10 to power n. And here I can think about n being from 2 all the way to infinity. Correct? I can think about this as being as n goes from 2 all the way to infinity. So I'm isolating this term by itself. I'm not going to pay attention to it at first. And then this part here, this is a geometric, infinite geometric series. And I can rewrite it as each term looks like 8 divided by 10 to some power, right? 8 divided by 10 to some power. And these powers range from 2, because this is 10 squared. These powers range from 2 all the way to infinity, correct? From 2 to infinity. Okay. So this piece, this is a geometric series. So this is an infinite geometric series with common ratio. What's the common ratio here? It's 1 over 10, right? 1 over 10. And, right, it's 1 over 10. Let me try to explain why. Because when you want to move from one term to the next, you multiply by 1 over 10. Or, right, if you want to go from here to here, you multiply by 1 over 10, and so on and so forth. Or equivalently, the quotient between two consecutive terms is simply 1 over 10. Okay? So the common ratio is 1 over 10, and first term is 8 over 10 squared. Correct? First term here is 8 over 10 squared. Well, since this is a geometric series with common ratio less, an absolute value less than 1, so let me take you back to that property above here, this property here. So since the absolute value of the common ratio is less than 1, then the infinite series is going to be convergent, and the total sum is going to be the first term divided by 1 minus the common ratio. Correct? So thus the series converges and its sum is first term divided by 1 minus common ratio, and in this case the first term happened to be 8 divided by 10 squared, and 1 minus common ratio, the common ratio is 1 over 10. Correct? So whatever this number is, it's going to be the sum of this infinite geometric series. Let's find that number. This is equal to 8 over 100 divided by, if you do the same denominator here, this is 10 minus 1, so 9 over 10. Correct? So I'm making the same denominator, meaning I'm rewriting 1 as 10 over 10. And if you have that common denominator, it becomes 10 minus 1, which is 9, divided by the 10. Okay? Alright. And this is equal to, how much is this? So that's 8 divided by 10 squared, that's the numerator, divided by the denominator is the same as multiplying by the reciprocal of that, which means 10 over 9. And this is simply 8 over 90. Correct? Because this 10 and 10 divided by 10 squared is simply 1 over 10. So this is 1 here. Okay? So what's the total sum of this geometric series? It's simply 8 divided by 90. So we get that this is equal to, so this is, let me separate them. Okay, so this is equal to, what's equal to? This number 0.7888 forever, which was this guy plus this sum, and we just found that this sum is simply 8 over 90. So we can rewrite this as 7 over 10 plus 8 over 90. Correct? And now if you make the same denominator, which is 90, so you can write this as 7 times 9 over 9 times 10, or 10 times 9, plus 8 over 90. Correct? I'm just making the same denominator here. 10 can be, you can multiply downstairs by 9, and you gotta do also upstairs by 9 to retain the value of this quotient, and this is the same as 63 divided by 90 plus 8 divided by 90, and this is 71 over 90. And this is in reduced form because 71 is a prime number and 90 is not a multiple of 71. Okay, so at the end of the day, 0.788888 forever 8 is equal to 71 divided by 90. If you try to divide 71 by 90 using a calculator, you're gonna see 0.78888, and at some point it's gonna round up. It's gonna put a 9. So which is a wrong answer, right? Because the truth is 71 divided by 90 is 0.78888 forever 8. Okay? Alright, I'm gonna leave you with an exercise which will be discussed in class, and this exercise is about showing that 0.9999 forever is equal to 1. And this was a promised exercise at the beginning of this course, and I told you when you have the tools you will actually be able to show it. And the way you're going to show it is you're going to treat it the same way as I discussed above that problem. You're going to rewrite 0.99999 forever 9 as 9 divided by 10 plus 9 divided by 10 squared plus 9 divided by 10 cubed, and you're going to observe that this is It's going to be an infinite geometric series with common ratio 1 over 10, and as such it's going to have a limit, it's going to have a sum, a total sum, it's going to be convergent, and this total sum is going to turn out to be a 1. Okay, so this is just to complete my promise, and with this I complete also this section.